complexity? How many training examples are needed to learn a concept? It depends, of course, on the hypothesis space, the space from which the concepts are taken. And as we found out, it also depends on who gets to choose these examples. We've discussed 3 different setups for answering the sample complexity questions and other questions of computational learnability. The 3 setups, if you remember, one of them was the learner gets to choose what question to pose next. This is like the typical scientist who gets to decide what question they're going to ask, subject to funding, of course, and then poses the question to nature and gets the answer. Second setup was the teacher gets to choose what question to pose. This is more like a teacher in maybe grammar school or a tutor teaching a child something. And then the third setup, which is where we're going to spend most of our time today, is when neither side gets to choose the questions, or neither side gets to choose the input examples of the questions, they come from some outside distribution, which we typically don't even know what the distribution is, we just know we can sample from it. The one thing we do assume is that the distribution is stationary, namely it doesn't change over time, although you could relax that as well. But even more important than that, what we know is that whatever distribution is used to get the training data will also be the same distribution used in the future to test the system. So we're optimizing our answer or our learning under the assumption that it will be tested under the same conditions that it was trained under. So not the same data, but data coming from the same distribution. Okay, that's an important assumption. So here is the setup we will be using from now on. This is what we call the third setup. We're going to be talking about it for a while, so I want to summarize it in a okay, good enough. You have a set of instances, call it X, a set of hypotheses, that's the hypothesis space H. Then there's a set of possible target concepts C. We didn't have that before. The reason we have that is the learning algorithm doesn't know C necessarily. It has H, which is the hypothesis space. C is the space from which our target concept, small c, is taken. If we're going to try to answer questions such as, are concepts learnable? We have to define what class of concepts we're talking about. Any one concept is trivially learnable by an algorithm that just outputs that concept. Right? Things become interesting when you tell the learner, I'm going to try to teach you something, a linear function, but I'm not going to tell you which linear function. And now I'm going to present you with examples and you're going to try to learn a linear function. So that class of linear functions is that big C. So learnability results are typically expressed in terms of this concept class C. You might hear somebody say that they proved that KDNF formulas are learnable. Or they proved that polynomial of up to third degree are learnable. What they mean is that if both the learner and the teacher agree that the target concept is a member of this class, then any member of this class would be learned, maybe with some caveats, maybe needing a lot of data, maybe only with high probability, but some statement is made about the likelihood of succeeding in identifying, namely learning, that member of the class. This is separate from the hypothesis space in which the learning takes place. Now, they might happen to be the same, H and C, but they don't have to be the same. Okay, then we have training instances that are generated by a fixed unknown probability distribution curly D over X. I've already used curly D with you guys before. We use regular D to denote a data set. We use curly D to denote a distribution from which the data set usually was derived by sampling. Now the way the game works is the learner observes a sequence D of training examples of the form X and C of X. C is the target concept or target function. C of X is the label, is the output, is the correct answer over X for some target concept in C. So conceptually, first the target concept small c is chosen from big C, and then training data is generated, and the target concept C is applied to all these training examples, and the pairs of input-output are presented to the learner. Instances are drawn from the curly D. Teacher provides C of X. Now the learner must output a hypothesis H that estimates C. So ideally it should predict exactly C, it could calculate C exactly, but we're going to talk a lot about the fact that in the real world we'll be approximating C and different notions of approximation. Now whether learning succeeded or not is determined by evaluating H, evaluating its performance on subsequent instances drawn from the same distribution curly D. So that's our famous test data, test set. So what's important here is that the instances are drawn probabilistically, but the classification itself is noise-free. Namely, it is assumed that both for the target concept and whatever the learner ended up with, the H that they ended up with, are both deterministic functions. You give them the same input, they will produce the same output. This does not have to be the case. You can think of trying to learn a stochastic function that doesn't always give the same answer. Or you can think of outputting a stochastic hypothesis. But that's not the case here. The target function is deterministic. The hypothesis that you're supposed to output is deterministic. The only thing that's stochastic is the data that you're exposed to. Even this last condition makes things a little complicated, because what does it mean to say that the H you produce is a good one? Presumably it means that it makes few errors, right? Ideally it shouldn't make any errors, but let's say it makes few errors. Maybe only 1% of the time it's wrong. But what do you mean by 1% of the time? One day you may draw a sample of 100 test examples and be wrong on one of them. Another day you may draw a different set of 100 examples and be wrong on 5 of them. And yet another day you may draw another set of 1,000 and not be wrong on any of them. So what do we exactly mean by, having a low error rate for the hypothesis? Suppose the algorithm gave you its answer, it gave you an H. How do you decide if that H is good enough? So the underlying criterion for H is its true error. Okay? Not its error on any one particular test set, but it's true error. Well, what is the true error of a hypothesis in this kind of setup? Is it the number of errors it will make if you tried it on every possible input? Yeah? Why are you doing this? It might not be possible to try it on every input. There may be infinitely many inputs.
We're also not necessarily interested in all inputs. We're interested more on the inputs generated by curly output.
Yes, that's the important point. We don't want to evaluate it on all inputs and weigh all possible inputs equally, even if we could, if we had the time to do all of that, because we view all possible inputs through the distribution curly D. Some inputs can be much more common than others. You can even imagine a situation where your hypothesis is correct on only a small fraction of the input space and incorrect on the rest, but that small fraction accounts for 99% of all examples coming from curly D, because curly D is concentrated in that small region. In that case, we would say that your hypothesis is pretty good. So we're evaluating how good curly D is how good H is relative to curly D. Namely, We're evaluating how well it does on average on examples drawn from curly D. The formal mathematical definition of it is the expectation of the error rate under curly D, or alternatively the expectation of the accuracy, 1 minus the error, on curly D. So here it is. It's called the true error of a hypothesis, and the square is our instance space, the space of all possible inputs. The pluses and minuses are the true labels, some examples, and you only show a handful of examples. There are many more. The space is filled with them. C is the target concept, the correct concept. Remember that concepts can be represented by subsets. So anything inside the C oval, the true label is positive, and everything outside the true label is negative. H is some hypothesis produced by our learner, and as you see, H overlaps C to a great extent, but not completely. In fact, they disagree on all the instances that are in this sliver or in this sliver. Is H a good approximator of C? The answer is we don't know, because we don't know where curly D concentrates its power. Where is most of the mass of curly D? If most of the mass of curly D is in these slivers, then H is a terrible approximator of C. So whether H is a good approximator of C or not depends strongly on what the distribution is that the input came from. It cannot be answered without that. So the definition of the true error of a hypothesis H, which we will write as error of the hypothesis H with the curly D as a subscript to remind us it depends very much on curly D, with respect to target concept C and the distribution curly D, is the probability that H will misclassify an instance that is drawn randomly according to curly D. So it's defined here in probabilistic terms, but you can also think about it as behavior over progressively longer samples, or expected behavior as the size of the sample goes to infinity. In a formula, it's the probability under the distribution of X coming from curly D that the correct classification is different than the classification given by H. This makes sense. There's only one problem. We can never calculate the true error exactly. Because as I told you, we don't have typically the analytical form of curly D. We don't even know what it is. We can draw from it, but we don't know how to write down analytically what that function is. Sometimes we do. Most interesting real-life situations, we don't. And if we don't know the shape of this distribution, we cannot calculate the true error exactly. However, we can approximate it. We can approximate it by just taking a sample drawn from curly D and evaluating the error in that sample. The error rate on that sample is not going to be exactly the true error rate. But if the sample is large enough, it's going to be close to it. So we talk now about two kinds of error: the true error and the test set error, which is the approximation of it. Now there's a third kind of error we can measure, which is the error on the training set. True error, test set error, training set error. Which one is likely to be the lowest? Training set error. Why? Overfitting. Yes, it is the hallmark of overfitting that the training set, that the true error, that the test set error is higher than the training set error. So whenever the difference between the two is significant, we say that's overfitting. Even in situations that we would not call overfitting, there would typically be some, hopefully small, well, I'll take it back, it doesn't have to be small. There could be a fairly large difference. So take, for example, decision trees. And if you remember, we decided where to stop growing the decision tree based on some held out set, right? And when the held out set error rate stopped going down, started going up, we said that's the onset of overfitting. We're going to stop growing the tree right there. But even if you stop right there, there is still a difference between the error rate on this validation set and on the training set. So there's no overfitting yet, but there's already a gap. Please.
A lot of learning algorithm targets to minimize the errors on training set. That is the
Right.
criteria.
Learning algorithms typically work by trying to minimize the error of the training set. If they do too good of a job, we have overfitting. But even if they don't do don't go too far, typically the learning that they do consists conceptually of two parts. Learning the generalizable relationship between input and output, the part that they're trying to learn, plus a little bit of learning the data set, the specific data set. They can't really avoid latching on to some of the idiosyncrasies, some of the peculiarities of the training set. So the larger the training set, the less pronounced this phenomena is. And the more careful you are with not getting overfitting and with cross-validation and with stopping on time, the less that would happen. But it would always happen to at least a small extent. So we have training set error, test set error, and true error. Now you told me the training set error is typically lower than the other two. What about the other two? Do you see, is one of them always larger than the other or smaller than the other? Is one of them usually larger or smaller than the other? True error and test set error. Please.
Well, test set error is also drawn at random from the, so they would be about the same as the true error.
Right. The test set error, if done correctly, is based on a randomly drawn sample from the true error distribution, the true error, based on the true error. So it should be distributed around the right value. There should be a caveat here. I said if done correctly. If you use a test set occasionally during the training just to test how well you're doing, if you use it as a validation set, and you make some decisions based on what you see, you consider the test set has been contaminated. It informed your decision. It informed the algorithm which way to go. It could be very subtle. Something as simple as deciding when to stop growing a tree. So the contamination may not be large, but it's still there. And as long as there's a little bit of contamination, you have a little bit of the same effect you have with the training set. In a way, the test set has become a little bit of a training set. So, example from decision trees. You repeat this experiment many times with many different data sets. You grow a decision tree based on some training set, and you decide when to stop based on some validation set. Pretty good. You repeat that many times, you find out that the behavior of the tree that you've grown on brand new data is slightly worse than its behavior in the validation set. Why? Because you use the validation set to make that small decision of when to stop. And therefore your decision is biased a little bit by the peculiarities of the validation set. We often use validation sets to just decide on one or two or three parameters. That's okay, but that's a tiny bit of contamination. So you could expect that the true error might be just a little bit worse. The only way you'd be sure that the true error is not worse on average than your test set is if you're using a brand new test set, if you have not used for anything else in this procedure, and you're not making any decision based on it except estimating the error. Now here's an interesting question. Suppose you don't use a test set, a separate test set. You only look at the training set error, which you know is an overly optimistic assessment of the true error. Can you nonetheless use it to bound the true error? Namely, if your algorithm succeeded in identifying a hypothesis that has zero error on the training set, can you use it to say something about the likely error on new test data? or the true error. We know that the fact that we managed to classify all the training examples correctly does not guarantee us that we will classify the future. That we do know. But do we have reason to believe, can we guarantee that we will do no worse than 5% error? Or if we can't guarantee, can we say it's very likely we will do no less than 5% error? So that could be a reasonable goal. And here's a more formal description of it. First, we'll introduce this notion of exhausting version space. Exhausting version space meaning you bring the version space down to a point where exhaustion version space is a goal, which I've yet to show you whether you can or cannot achieve, but it's a goal that says that the version space is now good enough that no matter which member of it you chose, all members are actually pretty good with regard to the true error. Okay? So remember, version space is achieved by eliminating members of the hypothesis space that don't agree with the training data. So at any one point, the version space contains only hypotheses whose training set error is 0. It would be nice if all of these members also had a low true error. If they all had a low true error, we'd be in a good situation where we could choose any member of the version space and it would be a good answer. Okay? So that's our goal. Exhausting the version space is our goal. Exhausting means getting rid of undesirables. Okay, so the formal definition is a version space which is parameterized by the initial hypothesis space and the data is said to be epsilon exhausted with respect to the target concept C and the distribution curly D if every hypothesis in this version space has error less than epsilon with respect to this target C and curly D. So this is just what I said to you in English. Our goal is to exhaust the version space. We will define some epsilon, maybe 5%, maybe 1%, and we say, gee, wouldn't it be nice if we could bring the version space down to the point where every member will have a low true error below epsilon. Well, we may not be able to do that, but we may be able to show that under some conditions, with enough training examples, maybe not every member has less than epsilon error, but the vast majority of members have less than epsilon error. If the vast majority is 99.9%, all we have to do is choose a random member from the version space, and with probability 99.9%, we will have gotten something we like. Okay? So there are two new concepts here. One is, we're no longer hoping to get a member that has zero true error. We are happy with an epsilon approximation, namely no more than epsilon error. The second concept, which is different, is that we're no longer trying to guarantee that we will find even an approximation. We're just trying to show that we're very likely to find an approximation. That whatever we find, very likely is a good approximation. Two different concepts. One is, our goal has changed to approximation, and the second is, our goal became probabilistic. We're not trying to prove that we will always succeed, but we're going to prove that, or going to show that we're likely to succeed, very likely to succeed. So, the way we're going to achieve that is by showing that any member of the version space that is undesirable, that has true error higher than epsilon, is very likely to be kicked out during the training process. This is more or less how the theorem goes. I'm not going to show you the theorem, it's due to David Hausler. I'm going to show you the theorem itself, I'm not going to prove it. The sketch of the proof is in the book, and it's not difficult to follow. But here is the theorem. The theorem talks about how many examples do we need to be able to say that we've cleared the hypothesis space of almost all undesirables. Suppose the hypothesis space is finite, and we have a sequence D of m independent random examples of some target concept C, and suppose epsilon is some small number, which is our threshold of approximation, then the probability that the version space with respect to H and D is not epsilon exhausted, the probability that there are still too many undesirables in it, is less than this number. Now let's look at this number. It depends first of all on the size of the version space. So this number tells you how many examples you need in order to, with high probability, clear the version space of undesirables. Okay? First of all, it depends on the version space size. The larger the version space, the more examples you'll need. But the relationship is linear. For a double the size version space, you'll need double the number of examples. Second, it depends. I'm sorry, this is not the number of examples. This is the probability. So, sorry, let me take back. I don't know what I was saying. I have M here and H here. What this is a probability. This is the probability that the version space is not epsilon exhausted. So this is the probability of something not good. This is the probability of us failing, in a sense, failing to achieve what we wanted. So we want to push this number to be as small as possible. Of course, the more training examples we have, the larger this exponent becomes, the smaller this whole thing becomes. Right? So with enough training examples, eventually we will achieve this goal. But what I said before is still true in a sense, in that the version space size plays a role here. The larger the version space, the larger M will have to be to push that probability of failure down below our acceptable range. Okay? So we chose an epsilon, which is our degree of approximation. We know the hypothesis space, so we know its size, and let's assume it's finite. And now we ask ourselves how many examples we need. And the answer is, if we want to bound the probability of failure below 1%, 0.5%, whatever you want it to be, we need to keep raising this M number, getting more and more examples, until this number becomes less than our tolerable probability of error. Now, if our tolerable probability of error is called delta, if we're willing to take a chance of, say, delta of 1% of failing, then we have this relationship between the desired approximation level, the probability of failure, the size of the version space, and the number of training examples. And you can try to isolate any one of these four, but the interesting thing for us to isolate is the number of training examples. So you have now a formula which gives you a lower bound on the number of desired. Now let me be careful if I say lower bound or upper bound. It's really neither. What it is it says if you set your desired approximation level and your tolerable probability of failure, and you know the size of your version space, then if you have at least this many examples, you will have succeeded in the sense that your probability of error probability of failure will be less than delta. Now you may be able to succeed with fewer than this many examples. But this many examples are enough to guarantee the conditions that you wanted. They're not enough to guarantee that you'll end up with a good approximation, right? They're only enough to guarantee that you have a probability of 1 minus delta of ending up with a good approximation. Look at this formula. You'll see it again and again in several other results. The interesting thing here is the form of the dependence. The dependence of the sample size is linear in the hypothesis, in the log of the hypothesis space, and in the log of the tolerable probability of error. And it's inversely linear to the approximation level. So we have two small numbers to choose. One is the degree of approximation, 1% error, is that good enough? And the other is the probability that we will fail, also about 1%. So you could choose 5%, 1%, 2%, but there's a significant difference between the two. The sample size depends much more strongly on the level of approximation you desire than on the error tolerance, the failure tolerance. If you want to reduce your probability of failure from 1% to 1/10 so this changes from 1 over 100 to 1 over 1,000, so it changes from log of 100 to log of 1,000, that's not as big of a change than if you decided to change your definition of what it's like to be a good enough approximation from 1% true error to 1/10 true error. Questions? Please.
So, if your hypothesis space includes learning real value parameters, you can't use this then?
No, this theorem is for classification.
Okay.
So your error is defined as the fraction of the inputs
But
in your
I'm
sample.
saying if the hypothesis space is
Continuous?
continuous, right?
Okay.
Then you can't. Can you approximate size of hypothesis?
Oh, absolutely. That's what we're going to do the rest of this lecture. And so this deals with finite size hypothesis spaces. And it's a very good question. What do you do when your hypothesis space is infinite size? It turns out there's a very nice generalization of this, and the formula looks very, very similar. Except you can't have this here, because this will be infinity. You'll have something else. Other comments or questions? Okay, so let's do a simple example. Suppose the concepts class we're trying to learn, the big C, is conjunctions of Boolean literals. This is the example that I showed you at the end of last class. x1 and x3 and not x6. Anything of this form. So this is a finite hypothesis space, right? We said if the hypothesis space is the same as the concept space, namely all conjunctions of all literals and their negations, then remember the size of that was 3 to the n, because every x1, x2, all the way through xn can either occur in positive form, occur in negative form as not x6, or not occur. Right? So you have 3 to the power of n. Now, suppose we want to come up with some kind of a learning algorithm such that the version space, after seeing m examples, is what's the term to use? I forget. Is exhausted, epsilon exhausted. Namely, every member of the version space is a good approximator. Good defined with regard to some kind of epsilon that we chose. So every member of the version space has error, true error less than epsilon. We use our theorem to decide on how many examples we need. The size of the version space is 3 to the n, so log of 3 to the n becomes n log 3. We then plug in, first of all, our approximation level. If it's 1%, that would be 1 over 1% would be 100. We plug in here how sure we want to be that we succeed, or what is the probability, what is the our willingness, what is the probability we're willing to tolerate of not fully exhausting the space. Now, if we don't fully exhaust the version space, it doesn't mean we failed. Suppose that we did not fully exhaust it, but still the majority of members are good approximators. Then if we choose randomly, we're still likely to get a good approximator. Right? So it's very conservative in the sense that requiring that the version space will contain only good approximators. And in fact, if we failed in that, which we will have a probability of 1 minus delta of failing, still we might succeed in choosing a member that happens to be a good approximator. Please.
The version space could become empty, right?
The version space could become empty. If it became empty, and assuming H equals C, that would mean there is no solution. So I don't think it could become empty if the examples already come from the target class. Right? So under our assumptions, it would not become empty. In the real world, it could, sure.
Only if H equals C.
I'm sorry? Only if H equals C, right. If H and C are not equal, for example, they could be even non-overlapping, then we'll be in big trouble. Yeah, it could very well become empty. Okay, let's take an even more concrete example with actual numbers. If you remember our enjoy sport problem from the very first lecture, if you remember, the hypothesis space size was 3 times 3 times 3 times 3 times 3 times 4, I think. Is that what it was? Yeah, it was the size of the number of those angled bracket hypotheses we could form. If you remember, the angled bracket hypothesis corresponded to conjunctions, and in each attribute we could either specify an exact value or a don't care. Remember that? Anyway, there was a number, a magic number that came out of it, which was 973 hypotheses. It may have been in your homework. If not, we did it in class. So this hypothesis space is of this size. Now let's say we want to assure that with probability 95%, that's the delta, or rather 1 minus delta, namely the likelihood of success. The version space contains only hypotheses that have an error of less than 10%. So this is not very strict. We're willing to tolerate 10% error. Anything that has less than 10% true error we call a good approximator. And we're further willing to accept 5% chance that we will not exhaust the version space with regard to bad approximators. How many examples do we need for that? You plug in the numbers and you get 98.8 examples, so you need at least 99 examples. There's only one problem. Do you remember the size of the input space? 96. So you need more examples than the size of the input space. It's kind of not a very useful result, is it? Not exactly comparing apples to apples here, because remember that these examples come from some random distribution. So if you get 99 examples from a random distribution, chances are you will not have seen the entire 96. But why bother getting a random set? Just look at all entire 96. I mean, it's clearly not a very useful result nonetheless. So this is to show you that this theorem, as clean and elegant as it is not a very tight bound. In fact, in reality, the kind of bounds it gives you are not very good, are not very useful, because they're very, very conservative, way overly conservative. One reason for that I already mentioned, and that is the goal you set for yourself of cleaning the version space completely, or almost completely from cleaning it completely from bad approximators is overly strict or ambitious a goal. You don't need to clean it up completely. It's enough that you clean it up to the point that the majority of members are good approximators. In fact, if you know that 51% of them are good approximators, and if it's a two-way classification, all you have to do is take a vote. Is that true? No. No, it's probably not true. It's possible that 51% are good approximators, but they make their errors in different places. And as a result, even if you take a vote, you will not necessarily get the right answer most of the time. Okay, so this is a beautiful theorem, very elegant, but not that useful. Nonetheless, let me show you a slight generalization of it. Is that Shai? That's your name, right? Shai pointed out that a lot depends on whether H is equal to C. Namely, whether the hypothesis space in which the learner operates is exactly equal to the target the class from which the target concept is drawn. Many times you're in a learning situation where you don't know that. Further, alright, let me just show it to you. So, our assumption until now was that the target concept is a member of H, which is even not quite as strict an assumption as C and H are equal. It could be that H is larger than big C. But we assume that C is always a member of H, An agnostic learner is one that doesn't make that assumption. Why is that assumption important? Because if C is a member of H, then it is always in the version space. Right? Because it will never be kicked out, assuming the examples don't have any errors in them. As a result, we're guaranteed that there will be at least one member in the version space that has 0 error on the training examples. Now, if C is no longer, I'm sorry, this is always true for version spaces. If C is no longer a member of, not necessarily a member of the version space, then we're going to relax what our goal is. Our goal is to find a hypothesis that makes the fewer errors in the training data. Namely, if C is not a member, it is possible that the version spaces, so I put it out, would become empty. So, but since we're interested in approximation anyway, that's not that big of a setback. So now, instead of keeping track of all the hypotheses that have 0 error and then trying to figure out what the true error on the, instead of keeping track of all the hypotheses that have 0 training set error and then figuring out what the real error is, we're going to do something a little different. We're going to try to find hypotheses that have the smallest possible error in the training set, not necessarily 0. And then try to use that to bound what the true error is. Okay? So instead of 0 training set error up to epsilon true error, we're going to say smallest possible training set error and that amount plus epsilon for the true error. So in that case, you have a very similar formula. There's some difference here. This is epsilon squared, and this is 2. So it is easier to bound the true error if you start from 0 error on the training set than if you start from some non-zero error on the training set. But if you have a non-zero error on the training set, if you want to bound the true error epsilon away from that, you'll need this many examples. Questions so far? Okay, so now let's try to apply this framework to the real world where the hypothesis space is typically infinite size. Maybe it's parameterized by real numbers, maybe it lives in some Cartesian space. The hypothesis space can be very simple and still be infinite size. For example, think of the space of all linear separators in 2 dimensions. So you think of the input space as a 2-dimensional space, and then every hypothesis corresponds to a line with plus on one side of it and minus on the other side of it. The kind of stuff that perceptrons can do with 2 inputs. It's a very, very simple hypothesis space, only linear separators, but it's still infinite size. So the theorems that we show here, as unhelpful as they were in the real world, they're totally inapplicable now, because they have in the formula the size of the hypothesis space, and the log of that is still infinity. Nonetheless, not all infinite size hypothesis spaces are equal. Some of them are more powerful or have a stronger representation power than others. What's the word I'm looking for? I don't know, descriptive, articulate. 2 hypothesis spaces can both have an infinite number of members, but one, discriminative, that's the word I'm looking for. But one of them could be more discriminative than another. So what we're looking for is a way of characterizing, quantifying how discriminative, how finely discriminative a hypothesis space is. What does it mean for it to be finely discriminative? It means that it can make fine distinctions. What does it mean for a hypothesis space to make fine distinctions? It means that it has maybe several different hypotheses that are very similar to each other but differ by a little bit. If you talk in terms of classification, differ by a little bit means that there may be two hypotheses that agree on all examples, but just one example, one input, one of them says plus and the other one says negative, says minus. These are the kind of fine distinctions we're trying to make. So here's an example. The input space is two-dimensional. So it's this board. One hypothesis space is the linear separators. And the second hypothesis space is any subset of the space, any contiguous subset. So an example from H1 would be this line with a plus on this side and a minus on this side. Let's say the input space is finite. It's exactly, not finite, it's infinite, but it's bounded in terms of x and y. So it's just this square. Every member of this square is a possible input. Okay, so this is x. So the separators are lines that go all the way. So this side is plus, this side is minus. An example of member of H2 would be something like this. What is the size of H1? Louder? What is the size of H1? How many members does H1 have? Infinite. What is the size of H2? Also infinite. They have the same size. In fact, those of you who know some set theory know that there are different degrees of infinity, but I assure you that these are both the same degree of infinity. Same number of members, so to speak, if you're willing to call infinity a number. But you could argue that H2 is more expressive, more discriminative, has more discrimination power than H1. It's easy to see because H1 is a subset of H2. Right? Because if this is a member of H1, then this subset here is a member of H2. So anything you can express with H1 you can also express with H2, but not the other way around. In fact, there's a lot more discriminative H2 is. This difference makes a big difference to learnability and to how many training examples you will need to learn a concept. Now, in which direction does this dependence go? Suppose you knew that the target concept is inside H for both of these cases, whether you're learning from H1 or H2. So suppose the target concept, so C1 equals H1 and C2 equals H2. So you're told which world you're in. And if you're in the world of C1, then you take H to be H1, to be the set of linear separators, and you learn in that world. And if you're told you're in the world of C2, where any contiguous subset is allowed, then you use H2. In which world will you need more examples to achieve learning? Which one will you need fewer examples? Please, then.
It's the same as in the finite case. The larger so it's H2. You will need more examples if you're working in H2. Because if your set is larger, then you will need more examples.
You will need more examples in the world where the hypothesis space is more discriminative. You almost said it's the same as the previous example because it's larger, but it's not larger. It's just more discriminative. It's the same intuition, absolutely. Because H2 has more discriminative power, it can make finer distinctions. You will need more examples to nail down which distinctions are important. Compare that to an even less discriminative model, let's say H0. H0 would be only linear separators that are vertical. This is an example from H0. Learning the right vertical separator is in a way an easier job than learning any separator, which in turn is an easier job than learning any contiguous subset. You want to say that there are many more contiguous subsets than there are separators, and there are many more linear separators than vertical separators. But it's not exactly true. There are infinitely many vertical separators. But intuitively, there are more. I mean, if you didn't take set theory, you wouldn't know. You would think maybe that there aren't more, but there are different amount of infinity. But really, mathematically, they are the same number of infinity. It's the same infinity. But nonetheless, H0 is a subset of H1, which is a subset of H2. And in fact, it's a very small subset of H1. It's an infinitely small subset of H1. And H1 is an infinitely small subset of H2. So these hypothesis spaces are very, very different in terms of their discriminative power, even though by counting they're the same. Can you see intuitively why learning the right vertical line is easy? You give a training example, you get an answer, plus or minus, that allows you to cut the space in two, right? If you know that this goes from, say, 0 to 100 here, if you're free to choose the training examples, you choose 50. If it's positive, you go this way. If it's negative, you go that way. You keep applying these examples, and with a log number of examples, you can narrow down your uncertainty to a very small range. You may never be able to nail down the exact vertical line, but remember, we're interested in approximation. That's if you choose the examples, but we're in a situation where we get examples drawn randomly from some curly D, but that's okay. We'll use these examples to narrow down the range, and then we can prove that with very high likelihood we have a very good approximator. Now try to do the same thing with regard to any linear separator, H1. You could do that, but it'll require many more examples. Because in addition to this kind of movement, you also have to worry about rotation. Now try to do it with regard to any contiguous subset, and you will need many, 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 many more examples. Because the space of contiguous examples is very, very large, and they could have very weird shapes. Okay? So the relationship is between the sample complexity and not the size of the hypothesis space, but its ability to make fine distinctions. Its richness. For any given situation, can you find multiple members of that hypothesis space that make fine distinctions in that space? That's the intuition. Now let me turn it now into math. You take a input space, and you take a few examples in it, x1, x2, x3, say. You have a hypothesis space in mind. You would like to know whether this hypothesis space is rich enough, discriminative enough, to make all possible distinctions based on these three inputs. Okay, this is the property I'm interested in. It's based on the intuition I just gave you before. If it does, you will say that this hypothesis space shatters these three examples. Okay? H shatters x1, x2, x3. What does it mean to shatter? It means that you can find, for any way of classifying these three examples, you can find some member of H that would do the job. How many ways are there of classifying these three examples? You can classify x1 as positive and x2 and x3 as negative. You can classify x1 as negative and x2 and 3 as positive, and every other combination. How many combinations do we have? No? 8. Thank you. So there are 8 different ways of classifying these three examples. If for each one of these 8 assignments there's at least one member of H that can do it, then we say that H shatters these examples. Okay? Now, suppose H does shatter these examples. I can now add a fourth example, call it X4, and say, can H shatter 4 examples? If it can shatter these 3, then naturally it can shatter any subset of 2 of them. But if it can shatter these 3, it doesn't mean it can shatter all 4. Because now we need to come up with 16 different members of H, each doing different combination. And if you can shatter 5, can you shatter? If you can shatter 4, can you shatter 5? Can you shatter 6? The more discriminative H is, the richer H is, the more it can shatter in general. Now it's possible that H can shatter these 3, but not these 3, for some hypothesis space, for some input space. So given a hypothesis space and given an input space, you still need to specify exactly which inputs are you trying to shatter. And it's possible that H can shatter many sets of 3 inputs, but not all of them. Or it can shatter only one set of 5 inputs, but not the others. It depends on the specific set. The game we're going to play is we're going to take a hypothesis space and try to shatter as many points as possible. So we're going to start with one input, and we're free to choose which one. But typically, shattering one point is trivial, right? It's easy to find a hypothesis space that calls it negative, and a hypothesis that declares it negative, and another hypothesis declares it positive. That's it. You shattered that one point. Then we're going to choose another point. We're going to have 2 points and ask ourselves, can we find 4 members of H that shatter it? If we succeed, we're going to move to 3. If we succeed, we're going to move to 4, 5, until we get stopped. When are we stopped? We're stopped when there are no, let's say we successfully shattered 4. We now try to shatter 5. We put 5 points on the board, or choose 5 members of the input, and we convince ourselves that H cannot shatter them. Maybe by showing that there's a particular assignment of pluses and minuses that is not consistent with any member of H. So we conclude that H cannot shatter these 5 examples. But wait, we're not married to these 5 examples. We can try different 5 examples. Let's try to change it to maybe put a different example here. These 5. Can H shatter these 5? We're going to look and look and look and not find a way to shatter these 5. Well, try a different 5. You're free to try any 5 that you want. If you reach the conclusion that there is no set of 5 points that H can shatter, that's the end of the game. Okay? That's the game we're going to play. Remember the rules. You can choose any set of K points. If you found at least one such set that H shatters, you get to move on to the next round. You get to move to K plus 1. When you can no longer do that, the last set of K that you shattered is called the VC dimension of H. And it is a measure of the richness or discriminative power of H. It is one measure. There are many other ways of measuring things, but it is one particular measure that would prove useful for bounding sample complexity. The VC dimension of H is defined as the size of the largest set of inputs that H can shatter. I'll make the important distinction again. It doesn't mean, if the VC dimension of H is K, it doesn't mean that any set of K inputs can be shattered by H. It only means that there exists at least one set of K inputs that can be shattered by H. And what does it mean for H to shatter these K inputs? It means that you can find 2 to the K members of H, such that each one of them makes a different assignment to these K inputs. Assignment of yes or no, plus or minus. So VC dimension of H measures the richness or discriminative ability of H. It is somewhat related to the size of H. Suppose you had a finite H. What is the largest possible VC dimension of a finite H? the size of x. Size of x is always an upper bound on the VC dimension of h, whether h is finite or infinite, because you can't shatter more than x points if you only have x different points. But it's not a very useful bound because the size of x is usually huge. But if you know that h is finite, let's say you know that h has only 1,000 members, only 1,000 hypotheses, what can you say about the VC dimension of h?
Log 2 of that.
Log 2 of that would be the upper bound. Let's say log 2 of 100 is 6 point something, almost 7. So the VC dimension of h cannot be more than 6, because for it to be 7, it should be able to shatter 7 points. But to shatter 7 points, you need 128 different hypotheses, and you only have 100. Okay? So VC dimension of h is less than or equal log the size of h. And I would say even floor of that. What if h is an infinite, which is the case we're really interested in? Then this bound is meaningless. It's less than infinite, less or equal infinity. But it's still possible that even though h is infinite, it has infinitely many members, they're not as discriminative as we'd like them to be. And therefore, the VC dimension can actually be quite small. It could even be 1, or 2, or 3. Question?
Is it always finite?
No. Good point. It is possible that as you played a shattering game, you started with an h that is so rich, that can express so many things, that you never stop the game. That no matter how many, any finite number of examples from the input space can all be shattered. In that case, we say that the VC dimension is infinity. So that would be the case if your hypothesis space is every possible function. Right, that's the case we discussed a long time ago when generalization is not possible. We have no bias. You have no bias. Any possible function, so there are 2 to the x possible, 2 to the x possible functions, where x is the size of the input space. In that case, the VC dimension is infinite because you can shatter, if x is a finite space, then VC dimension would also be finite, because you cannot shatter more than x points, because there are only x points. But let's say you're in a situation where the input space is infinite, some continuous space, and any function, including non-continuous functions, is allowed. Then the VC dimension would be infinity. Okay, why do we want the VC dimension? Because it turns out that for infinite size hypothesis spaces, it plays the same role as the log of the size of h in a finite case. So it's a generalization. You can think about it roughly as being more or less the log of the size of the space, except it's a generalization of the notion of a log the size of the space to cases where the space by counting is infinite, but the discrimination power is actually finite. So if you remember the theorem I showed you of the sample complexity, how many examples m do you need in order to guarantee with high likelihood that you will get a good approximator? And that formula depended on the log of h. I want to show you a very similar formula for infinite spaces. And maybe I should compare it to the previous formula we saw. So let's start with this one. This is the formula we saw earlier for number of examples you need based on the degree of approximation you desire, the size of the hypothesis space, and the probability of failure that you're willing to tolerate. Now, exactly the same situation, but with infinite version spaces. You have the same dependence here on epsilon, the approximation level. You have a very similar dependence on the tolerable probability of failure. Here you have log of 1 over delta. Here you have 4 log of 2 over delta. Very similar dependence. Here you have log of the size of the hypothesis space. Here you have something that depends on the VC dimension. So the VC dimension is similar to the log of the size of the hypothesis space. And there's another component here that has to do with the error. So it's not exactly the same, but it's a very similar flavor. So all this is by way of motivating why we need a VC dimension. Of course, I didn't show you the derivation of this theorem. I don't think that is even described in the book. I should tell you that this is about 20 years old. This whole theory was developed in the mid-80s, was pioneered by Leslie Valiant at Harvard University. His main contribution had to do not so much with the VC dimension. VC dimension came from two other gentlemen, Vapnik and Chervonenkis. This is where the VC comes from. The contribution of Valiant came from contributing this notion of we're going to look for an approximation and we're going to allow some probability of failure. Okay, these two different dimensions that I talked about. Instead of we're going to guarantee that we get the right concept, we made two concessions. One is we're not looking for the right concept, we're looking for a good approximator of the concept. And two, we're not going to guarantee that we get it, we're going to show that we have a high likelihood of getting it. This is the contribution of Valiant, and the whole framework he's created is called probably approximately correct learning. Probably approximately correct. Let me write it and write the epsilon and delta next to it. So first of all, the approximately. Approximately is related to our epsilon, the degree of desired approximation. If we could guarantee that we will end up with a good approximator, that would be very, very nice. But even that we cannot guarantee. What we can do is say that we're very likely to end up with a good approximator, and that's where the probably comes in. And the probably has to do with 1 minus delta. Delta being the tolerable probability of failure. So with probability of at least 1 minus delta, we will get an approximator that's epsilon good, epsilon close to the truth. Probability of approximately correct goes by the acronym PAC. So PAC learning is the whole framework of probably approximately correct learning, developed by Leslie Valiant in, I think, '84, in a paper called The Theory of the Learnable. It was the first time that anybody was able to derive a mathematical result that said something meaningful about are we going to succeed in learning. Until then, machine learning was pretty much a heuristic-based discipline. You tried things, and maybe they worked, maybe they didn't, maybe you showed that they worked most of the time, but you couldn't prove anything about them. So it was quite a paradigm shift. Then Mr. Vapnik and Mr. Chervonenkis came around sort of separately and try to characterize make fine distinctions with regard to discriminative power of different infinite size hypothesis spaces. So they came up with this way of measuring it, and I should tell you there are other ways of measuring. And then Hausler came around and showed the result about, that was '88 already, showed the result of cleaning a version space from undesirable approximations, from bad approximations. And then all these three could be put together, relating VC dimension to clearing a version space to probably approximately correct learning. So what I'd like to do in the remaining of the time is do with you some examples of calculating VC dimensions of different hypothesis spaces. And this is the kind of things that you will probably do in your homework. do go over not just the book but the slides. They're very helpful, I think. So let's start with the linear separators. What is the VC dimension of the space of all linear separators? Like what I showed here, this line. We're going to play the game as I defined it, of stun, point, shadowing it, moving to 2 points, trying to shadow that, moving to 3 points, and so forth. So 1 point is very easy to shatter. Here you have x1. To shatter it, you just need to show 2 members of H, one that classifies it as positive, one that classifies it as negative. That's very easy. There are many such members. This line with a plus on this side classifies it as positive. This line with a minus on this side classifies it as negative. In fact, you could use the same line and just reverse the plus and minus to classify it once as positive, once as negative. That's trivial. So let's move on to 2. And on the side we note that the VC dimension of this space is at least 1, because we shattered 1 example. Now let's put 2 examples here. Let's choose this one and this one. Now I need to find 4 lines that classify it all possible ways. That's easy too. Put 1 line here with a positive side going this way, another line here with a negative side going this way, another line here with a positive here and a negative here, and another line here with a positive here and negative there. Very easy to put lines that do all 4 possible combinations, right? So VC dimension is at least 2. What about 3? Here are 3 points. 1, 2, 3. Nice straight line. Can we shadow these 3 points using all linear separators? It's easy to classify all 3 of them as positive. It's easy to classify all 3 of them as negative. It's easy to classify this one as positive and these 2 as negative, or this one as negative and these 2 as positive. Easy to do it this way too. But what about classifying this one as positive and these 2 as negative? Is there a line that would do that? Straight line. No, there isn't. Does that mean we cannot shadow these 3 points? Yes, it does. It does mean that. We cannot shadow these 3 points. Does that mean the VC dimension is 2 and not 3? No, it doesn't mean that, because maybe we can shadow a different set of 3 points. So what about these 3? Can you shadow these 3? 1, 2, 3. The answer is yes, easily. It's easy to put a line that puts one of them on one side and 2 on the other side, and all possible combinations. So VC dimension is at least 3. What about 4? Can you shadow 4 points? Now if I gave you a set of 4 points, and I proved to you, well, put it here, that you cannot shadow these 4, that doesn't help you that much, because maybe you can shadow another set of 4. So it's a little trickier. You need to somehow convince me that any set of 4 cannot be shadowed. Can you do that?
Can you give an example of sort of non-linearly separable points?
Okay, so for these 4, for example, if this is positive, this is positive, this is positive, and this is negative, that's non-linearly separable. There's no line that puts all 3 on one side and puts this on the other side, right? So you proved that these 4 cannot be shadowed. But can you prove that no 4 can be shadowed? Yes?
Just in all the cases that these points there are only 2 points on the line, or there is one, there are 3 points on the line, there are 4 on the line.
Okay. So what you're suggesting is that you break all possible choices of 4 points into some categories and prove it for each category separately. And that can be done. For example, there's one category that says that 1 point lies inside the convex hull of the other 3. Right? If you connect 3, the 4th one will be inside. These cannot be shattered because you cannot assign the outside one label and the inside a different label. The alternative is that if no point lies inside the convex hull of the other three, that means they form a convex polygon. There's another possibility, which is the one you mentioned, which is three of them are in a straight line. But we know these cannot be shattered already.
What if you draw an arc, like a quarter of a circle, and you just pick 4 points on that arc?
Uh-huh.
Is it possible? It seems possible to me that any one of those points could be classified different by basically drawing a tangent line and then just moving it in a little bit.
Okay. I like your intuition, but I believe you're wrong. So I'd like to show that to you, but I want to use the half minute that's left to look at one other example. Okay? So, so I can't look at another example. I don't have enough time for the two examples I want. So what I'm going to ask you to do is to look at the examples in the book, and you will have examples in your homework. But the name of the game is always the same. You start with a few examples that you can shatter, and then you get to a point where it's not so trivial for you to find examples that you can shatter. You get to a large enough K where you can no longer, it's not easy for you to shatter. You put K points down and you look at them and you say, oh, I can't shatter those. Now is the tricky part. Now you have to prove that that's the case no matter what K points you choose. That's usually the hardest part. Once you prove that, you've found what the VC dimension is. Okay? If you can stay after class, I can discuss that with you. All right. Thank you.